Yeah. Okay, this is better. Okay, maybe too loud. Okay, how is everybody? Good morning. Good morning. How many of you are the outside registered participants? Almost everybody. Good. Good to see you all. And who is like, who thinks they're from the farthest? Who is from Mumbai? Who has come from the farthest? Tell me some state names. Jammu. Welcome. You? Yeah. Yeah? Jharkhand. Anything farther? Farther east maybe? Delhi University, that's far enough. Good, welcome to all of you again. And I hope everybody is excited for the day. We have some fantastic speakers. We have our own faculty. We have a few invited speakers from outside. But mainly, it's also our department's, sort of expo here. And you'll hear from a lot of our own students. And so let me get started with, of course, a welcome to this symposium. And I just want to, it's like when there is a big concert, there's a warm-up band, right? So I'm just the warm-up band while people are coming in here. So just to throw some stats and some ideas at you while we wait for the main speaker. So we are a pretty big department, 46 faculty members now. About more than 1,000 students, lots of staff members, huge buildings. You will see both these buildings as a part of the events today. And we have been in this Institute of Eminence list of universities since 2018. And in fact, this event is possible because of the funds we get through as part of being one of the Institutes of Eminence. So what is generally the picture of research at CSE Department, IIT Bombay? We have been organizing ourselves into roughly 3 streams recently. One is computing systems, which is questions and problems related to infrastructure, sort of the hardware, operating systems, cloud, networks. Everything lies here. Also, very sort of systems-heavy applications lie here. Then we have, of course, the intelligent systems, which is also known as AI, ML, and so on. So it's all about making computers closer and closer to thinking like intelligent beings. And then there is theory, which is the foundation for everything, every single thing. It encompasses everything, fundamental questions and problems of what is possible within some limited time, and things like that, and really sort of fundamental problems. And you can see that ellipse is everywhere. We actually currently have a course in the department called the Theory of Machine Learning. So it's everything. Yeah, this is again another list of the same things. We divide our intelligent system streams into these 3: speech and representation, visual computing, then networks and systems, architecture, compilers, all of this is systems, and we have algorithms and complexity, and then formal methods. And then we have a couple of arcs that are actually encompassing all of this. Digital trust, which is a domain which encompasses everything, and computing for development is more possibly in the first 5 things. There are sort of applications. Of course, work here results in some algorithmic work also. So this is just a picture in terms of how we are sort of distributed. We are fairly equal in terms of faculty, in terms of in what we do. PhD students, of course, you can see the trend, but we are fairly well balanced here. So I had just wanted to give an overview, because I'm hoping that many of you are here to find out not only what CSE department does, but what is research about, and how can you be a part of it. So a quick review here. I always like to say research is about asking the questions first. If you can get the habit of asking questions, then and more questions, you just have to ask the sub questions, and actually that kind of leads you to the answer. So get into the habit of asking questions, and also whatever work you are doing, get into the habit of saying what is the problem that it is solving. You're just doing something, but why? So what, why, what, how, when, which, where, can something. This is what research is about, and this is what hopefully you will see. And I just wanted to go through some examples very quickly. They are sort of related. They are not exactly what the talks and posters will elaborate, but these are just sort of I have like 10 or 12 questions out of the probably 100, 200 threads of questions and problems that our faculty and students are working on. Okay, I'll start with digital trust, and this might be a little naive. In 10 minutes, Professor Shweta is going to talk much more deeply about the theoretical aspect of digital trust. So this is just one sample problem. There are 3 people, Amar and Anthony, they want to buy a car which is for 10 lakhs, and but they don't want to tell how much money they have individually. Can you do that? Can you ask, can you figure out whether the sum is enough without knowing the individual? This is the kind of questions that this field asks, secure multi-party communication, whether you can compute a function while keeping the inputs private. So this is one of the threads that is going on, and some work that has been done here. I just wanted to continue this story a little bit. The same question has some other theoretical underpinnings. A formal methods thread of research can ask the question of, can such a protocol that is developed for this purpose be formally verified? Similarly, you can ask a question that, what is the complexity of that protocol? Then moving on to computing systems, the kind of work that is going on here, one is about architecture, making computers efficient at the architecture level. So one question here is, can we cleverly prefetch critical data, which is basically, critical means it can have processing stalls, from low bandwidth DRAMs in many core systems. So what is the answer? Maybe related answers you will find today. For this, you have to see the paper that was published. Then compilers, we have a question such as, can we make just-in-time compiling more efficient by reusing compiled code from a previous run? It seems a little, contradictory, but maybe you can do it cleverly. Then in OS and virtualization, a lot of things are going on. One sample question is, how can we make container migrations use less CPU? Currently, they're very CPU heavy. In networks, there's a very large project going on in the department, which is about optimizing 5G components. It's a part of a big project. Actually, a lot of IITs are involved. IIT Madras is involved. ISC is involved. So can we optimize 5G components so that data throughput is almost at line rate, meaning you're really meeting the physical rate that is capable for the line? Then in computing for development, we have some really good threads going on. There is computing for climate resilience in agriculture. So can we predict how vulnerable farms are to dry spells? You might ask, like, what has this got to do with computing? It absolutely does. It is basically data analysis, being able to work with satellite pictures, maybe not such good pictures, data, maybe not complete data. So finally, it becomes a computing problem. Then transport planning, of course, it's a classic computing problem. Can we improve Maharashtra road services using, again, prior data, geospatial data? Then we have, of course, lots of things. This is a very small representation of what's going on in the overall field of intelligent systems here. There is one thread is in the visual computing aspect. There is medical imaging. Can we segment objects in the medical image with less supervision? Like, can you find which part is the lung, or maybe something in the lung, things like that, okay, with less supervision data. Then there is speech recognition. This, how can we recognize the code switch? Code switch यानी मैं अभी जो कर रही हूँ वो code switch होता है, right? So in English, while we don't have enough data, lot of issues in intelligent systems boil down to not having enough data in our own languages. So that's one thread of work. And then, of course, there is a big, nice, very successful project going on in transport planning in scheduling of railways. Earlier, it was more about geospatial data and maybe conventional techniques. Here, intelligent systems-based AI/ML techniques are being used for scheduling. What happens with all of this work? One very common outcome is publications, and we are doing quite well in the publications. There is a convention in publications to aim for sort of what are called top tier fora, and if you come here to do research, that's what you should aim for. But other result is also translational research products, and this is sort of even the earlier is good for the nation. It makes us well known in the world, but this is more directly useful. For example, we have a product that was done out of this department called Jalatantra, which is for planning of the water distribution network. Again, it turns out to be kind of a optimization problem and can be done with computing. So this is actually being used in lots of states. And then all these other ones also that I talked in as part of the computing for development. Lot of things going on here that we want people to actually use. Again, the outcome of some of these things is lot of honors and awards for the faculty. I don't really want to go through all of this. You can check our news and our social media. And we have another thing that happens when you do well in a certain department, people open like big labs and stuff like that. So that has happened recently. We have a big thing called a trust lab. We will have a talk about this, I think today or tomorrow. I can see the schedule. And also GIC, this is a geospatial hub. And I think many of you might already know about eYantra. This is a project by Ministry of Education, and we do a lot of competitions and so on, very, very successful. So this is, but the point is that the engine for all of this work is really the students, and the ways that the students contribute to all of this is through these 3 research-oriented programs. Although I must say as a footnote here, our BTechs also contribute a lot to research, but this current audience, I want to talk more about the PG programs. So we have MTech, MS and PhD. MTech, you can find out more about it, we'll have some info booth later, but MTech is a conventional fixed duration program. It also, by the way, has a pretty serious, almost 13-14 month thesis, okay? So doesn't mean that it is not research oriented, but it is more fixed. We have made MS a little more research oriented in the sense that you start research right from your first semester, and it is flexible so that if you're working on a slightly hard problem, let's say some theoretical problem or even something in systems that is just taking time to sort of think about, then there isn't a clock that ticks. There's a clock that is a little more flexible. Whenever you are done, anywhere from 1.5 to 3 years, you can write the thesis, it gets externally reviewed, and then you can go. And PhD, of course, is the flagship program, and these are the people who do most of our research for us. Yeah, MS also, I want to, although PhD, of course, it's obvious, but MS is a new program, so I just want to say that we are having good publication success, and also applications and so on are being developed by these students. And we have lots of awards and everything. If you come here, you should aim for these sort of things. One thing is that government and industry is doing a lot. Everybody recognizes that we need PhD students, we need students who do research. So very good fellowships are there, making it a compelling choice. Don't just join a job, maybe come and do a PhD. Yeah, we have a lot of facilities and all this we'll see. Later I want to sort of wrap up for our next talk. I do want to say that when you do research, you are like almost like a full-time research staff member, and you get a cubicle in a nice lab. You're supposed to be hanging around there the whole day, and that's what we enable for all of you. Yeah, and faculty and research, we have a beautiful lounge. There's so many people that we couldn't take you up there, but if you join here, then there is a terrace lounge that research scholars use. So that's it. I don't want, it's more like I don't want to talk about it much. You are going to listen to, work done here, and also our very eminent invited speakers. So my last appeal is, choose to stand out from the crowd, be a knowledge creator, not just consumer. We are too much just consumers. We have to create, build things, innovate, disseminate, and find your sort of special place on the planet, really, by doing this stuff. And join our or any, I would say, this thing really is, our is a big thing. First appeal would be anywhere in India, but in general, anywhere. Just please do research. It's something that the whole world needs. So this is our admissions page. It's please watch the space. There is some link here, but it's there, linked from our website also if you want to find out more. We'll be adding the current year's data soon here. And that's it. Hope to see you here or any other IITs or ISC or anywhere as master's students and research students, really. Okay. So welcome again, and I'll give it to the MCs now to introduce our invited speakers. Thank you.
Hello.
Maybe you can just tell who I was. I didn't tell them.
Hello everyone. Thank you, Professor Varsha. So I didn't get a chance to introduce her. She is an amazing researcher, inspiring academic, great teacher, and the head of the Computer Science and Engineering Department at IIT Bombay. Hello everyone, I am Ashita. I'll be your host for today's event. Thank you Varsha ma'am for starting this event with such an insightful commencement address. Without further ado, I would just like to dive into the heart of RISC. Let me express my gratitude to all of you for being here in this exciting event with us. It's my privilege to introduce our first keynote speaker. She is Professor Shweta Agrawal from the Computer Science and Engineering Department at IIT Madras. In the world of cryptography, Professor Shweta Agrawal is an esteemed and distinguished researcher. She earned her PhD at the University of Texas at Austin, and she did her postdoctoral work at the University of California. Her extensive research in cryptography and information security, with a particular focus on post-quantum cryptography, has earned her numerous accolades, including the Swarna Jayanti Award and the ACM India Award for Outstanding Contributions to Computing by a Woman. She has received Best Paper Award at Eurocrypt, Google India Faculty Award, BY Award for Excellence in Research and Teaching, and she has been an invited speaker at prestigious conferences like Asia Crypt and Women in Mathematics. Ronald Rivest, a famous cryptographer and computer scientist, once said, "Cryptography is about communication in the presence of adversaries." Today, in her captivating talk, Professor Shweta Agrawal will guide us through the intricate dance between the possible and seemingly impossible within the world of cryptography, the art of negotiating with the impossible, as she aptly puts it. Please welcome Professor Shweta Agrawal.
Can you all hear me at the back? Is it working? Can you hear me now? Okay, great. So it's great to be here. Thank you all for coming. Thanks to IIT Bombay for the invitation. I'm really excited to talk to all of you. And thanks for the kind introduction. So indeed, I'm very excited not only to be here, but you know, from Varsha's introduction, I see that many of you are students who are thinking about a research career. So it's truly exciting and a privilege for me to introduce you to this beautiful field, cryptography, right? So cryptography is the art of paradox. How many of you have had a little bit of exposure to cryptography? Okay, so that's good. So a few of you. Let's just sort of jump right in. This talk is going to be really at a high level, and I encourage you all to ask me questions as and when they come up. Okay, so we have an hour, but we're not going to try to cover any ground. We'll just talk and we'll stop in 1 hour. Okay, so how does that sound? So please ask me questions, or you know, if you have comments anytime during the talk, please do speak up. It's always more fun like that. So cryptography is the science of keeping secrets, and actually as we heard in the introduction, you know, there was one definition of cryptography about, you know, communicating secretly, but really in the modern world, cryptography has grown so much bigger than that. Okay, so there are lots of really amazing, very surprising applications that cryptography enables. The first one, which is actually considered the most basic one, but which staggers me even to this day after more than a decade of research in this area, is this idea of exchanging secrets within a crowd. Now, most of us have heard the term encryption, etc. And you know, nowadays when we talk about this exchanging secrets in the crowd, people are like, yeah, I mean, isme kya hai? This is, you know, just encrypt. But you know, for this talk, in fact, I mean, for any kind of research, it's good to put aside ideas of what we know and just think from very basic first principles, okay? So this is the stage. So we're here today. I'm here, right, with a mic. Most of you are meeting me here for the very first time. And now let's say that, you know, there's one person with whom I decide that I want to communicate in secret. Let's say the girl in the blue over there, okay? And the only channel of communication I have is this microphone. Everything that I say can be heard by everybody, okay? And everything that she says can also be heard by everybody. We've never seen each other before. We've had no prior communication of any sort. Just in this moment we decided to speak, and we want it to be the case that though everybody can hear everything we say, somehow only the two of us can figure out what is actually being said. There's some secret in there. Do you think this is possible? How many of you think this is possible? Okay, very good. So the last time that, I gave some outreach talk, and similarly people said, yeah, this should be possible. I actually abandoned my slides and spent the whole hour convincing you why this should not be possible at all. Okay, but for the sake of the organizers, I will not do this today, but if you run into me again, beware. So this is super, super surprising. And oh, you know what, I can tell you an interesting anecdote. So recently I was at this Pingla Interactions of Computing, and there we, I was discussing this, this notion of exchanging secrets within the crowd. And there was a Turing Award winner there, a senior gentleman, and he did not actually know of this particular notion. And after the entire event was over, right, he finally, when he understood what key exchange enables, his jaw dropped open. Okay, so I'm just trying to tell you that this is very surprising, and the fact that you think it should be possible means that you have to think again, okay? But I won't say anything more about this. Another thing that it lets you do is it lets you prove to somebody that you know something without telling them what you know. Now let me give you an example, okay? So now let's say that, IIT Bombay, since they're into so much fun, they hand out these Sudoku puzzles to everybody, okay? And they promise some big money to whoever solves it first. So of course I want the prize, and I claim that I've solved it. Okay, so as soon as Varsha gives me this puzzle, I take a look at it and I say, I have the solution. Now I want to convince everybody that I actually do have the solution. Generally, how do you convince somebody of such a thing? You show the solution, right? So you can show the solution, everybody can verify it, right? But here I'm not allowed to actually show you the solution. So I don't, I need to convince you that I have the solution, but I'm not allowed to show you the solution. Is it possible for me, without cheating, to prove to you that I have the solution without telling you the solution? Is it possible? So maybe after all my threats in the previous bullet point, now people are more afraid of saying it's possible. It should not be possible, but cryptography makes it possible. Okay, so again, we don't have time to go into this, but it's another one of these really fantastical things that cryptography allows you to do, which is why in the abstract of this talk, I said, it's really about negotiating with the impossible. It's like, oh, you want to do this thing? This does not sound like it should even be possible. Cryptography says, let's do it. Okay, so it's really a beautiful field, yeah?
Going back to the first one, there is some implicit assumption about the physical properties of the medium.
Just air. I mean,
Yes,
we're assuming this medium.
What if, for example, if you can measure the distance between speaker and receiver accurately?
No, we're, just.
Yeah, so that's what I'm saying. There are some implicit assumptions about the physical medium you're making.
I'm talking of this room today.
Yeah.
Here. So
Correct.
This is my medium. That's my assumption.
Yeah.
I came here and this is my room. Let's say we want to talk.
Suppose there is a technology by which you can measure the distances accurately.
Okay.
Okay. And hence you know the distance to the blue girl. And using that property, you can figure out an encryption key and then proceed with your communication.
Okay, let's take this offline. I mean, what I have in mind, so we're veering very close to me abandoning this. This is exactly what happened last time. So everybody was like, yeah. And then at the end of the talk, everyone was like, no, okay. Let's take this offline, okay? But I just want to say that it's actually the assumption that you're really making is that the universe permits asymmetry in computation. Okay, we will be talking about this more in the rest of the talk. So let's get back to it later. Okay, yeah, great question. Anything else? Okay, so let's keep going. Another thing which is sort of, more, these first two are more classic applications. A much more modern one is, you want to run machine learning algorithms, but on data that is encrypted. Okay, we'll talk more about this in the next slide. And another one of my favorites is encoding a message which can be denied later. So let me also we'll also take a deeper look at this. So cryptography is really a field of indisputable utility. More importantly, really indescribable beauty. It's really like a game of chess where you always have to be one step ahead of the attacker, okay? So never a dull moment. So let's come to this application I told you about computing on encrypted data. And let me read from an article that appeared at Nature several years ago. The dream for tomorrow's medicine is to understand the links between DNA and disease and to tailor therapies accordingly. But scientists have a problem: how to keep genetic data and medical records secure while still enabling the massive cloud-based analysis that is needed to make meaningful associations. Okay? So personalized medicine is really a poster person application. So I think everybody agrees that medical research is very important, right? And we'd like to contribute to it. Now, people have genetic data with them, but it's also something very, very private, right? So you don't want to just hand it over. You don't really trust what people are going to do with this data. So can you run some sort of algorithm which allows you to compute what you want? Like let us say, the correlation between some pattern in your DNA and some disease or something like that. But while the data is still encrypted somehow. So, the data is hidden, but you're still getting what you want out of it. Sounds impossible, right? Okay. Here's another thing. Okay, so activism with safety. So this is what I mean. So let's say that, I'm in a regime where there's oppression and I want to organize a revolution, right? So of course this has happened, it keeps happening, it's still happening. So let's say that I want to encrypt some message, but it's something which is very dangerous. Now let's say that I've encrypted something like that. Here one thing to note is that encryption is a probabilistic algorithm, so there's some randomness there. And now somebody comes and puts a gun to my head and says, you published this ciphertext, open it, right? What can I do? Well, a hope would be that under coercion, I can reveal some fake random coins R prime. So remember, I encrypted using some R and I got some C. And under coercion, what I'm doing is I'm actually giving you some fake random coin R prime, which somehow lets me explain the same ciphertext as an encryption of some very benign message. Okay? So this is this notion of deniable encryption. Yeah, we won't talk any more about it. It's just another very surprising application. So in this talk, right, I've hopefully convinced you that cryptography allows you to cook up all these really amazing things. And today what we'll do is we'll talk or kind of take a little peek at how we do this, right? How do we prepare all these fantastic things? Okay, so that's what it will be about. And as a case study, we'll take sort of the most basic primitive that everybody knows about, which is just encryption. Okay. So encryption, as you already know, I mean everybody has, let's say, a public key and a private key. So my public key is known to everybody. My private key is known only to me, right? If you want to send me a message, you'll encrypt it using my public key and I'll be able to decrypt it using my private key. So everyone's familiar with this notion of encryption, right? And there are really two properties that we want from any encryption scheme. One is functionality or correctness, which means what? Well, if I encrypt something, somebody should be able to decrypt it. Otherwise, it's useless, right? And security is that the ciphertext should leak no information. So if I don't have the secret key, I should be able to learn nothing about the ciphertext. Okay, and really cryptography is about walking this fine line, right? You want functionality together with security. A little bit of thought will show you that these are really opposing requirements. Okay, any one without the other is easy. So functionality without security is definitely easy. Don't do, don't encrypt. Security without functionality is even easier. How? Yes?
Is it really possible that the key we are sending to the medium is actually not released by the medium, because medium itself somehow getting corrupted? In that case, what should we do in that case? Like, there is a 100% guarantee about secrecy, because in previous slide you
Okay,
mentioned.
so I think if let me know if I understood your question correctly. I think the question is that how much guarantee can you have that the secret key is indeed secret, right? This is the
medium
question.
also have its own secret.
Medium,
yeah,
there's
medium inside, medium inside.
There's no medium. Okay, so I'm running this setup algorithm. I generate a public key and a secret key. I just keep the secret key with me.
How we store in it? In where we store that key?
In my head, let us say.
Then in that case it doesn't leak, but
You can write it on a paper and keep it with you.
We talk about machines, so in that
Okay,
case.
so we're going to assume that we generate our own secret key. This is for simplicity. So I should say that in practice you're right that secret keys can get leaked and one has to worry about that. Actually this touches upon an important aspect of cryptography, which is how you model security. Okay, so here in the modeling that I'm presenting, we're really assuming that the secret key is completely secret. It is possible in the real world, like there are these things called side channel attacks and so on, through which some bits of the secret key can get leaked. I mean, people can call me and ask, say something about my parents being in danger or something, and maybe I'll just panic and give the secret key. So there are lots of ways in which keys get leaked, but we're not going to talk about that. Okay, so we're going to, for the purpose of this talk, and in fact for the purpose of almost most practical scenarios as well, it can be assumed that the secret key is kept secret. You can store it in a trusted hardware, okay, or you can store it in a machine to which only you have access. There are multiple ways of vaulting the secret key. Okay, so let's not worry. Does that answer your question?
Can we say that nothing is secret? What? Can we 100% say that nothing is secret?
Everything
should be leaked.
So if you, very good. So if we say that nothing is secret and everything should be leaked, then actually any sort of secrecy is impossible by definition, right? Because if I have to protect something against somebody, there has to be some asymmetry between my legitimate receiver and an eavesdropper, isn't it? I mean, let us say I want to protect my information from you, but I would like to send it to Preeti here. So there has to be some difference in information between Preeti and you, right? If both of you are looking at the same object and both of you have the same computational resources, then obviously it's not possible to get secrecy against one and not the other. So this raises an important point. It's worth emphasizing that we really need some asymmetry. So in information theoretic cryptography, which is another field of cryptography, we can assume that maybe we assume that the attacker is further away. The channel between me and the attacker is worse than the channel between me and the legitimate receiver. That's an assumption. Another assumption you can make is that the secret key is kept secret. Or even if there is leakage in the secret key, I assume that let's say only up to 50% of the key is leaked, but I have to make some assumption. Okay, yes?
Yeah, since you're mentioning caveats, should we also say that we are worried about generally when we come to computing, we think of computing as like 100% perfect, but all these algorithms, as you alluded to, are probabilistic.
Yes.
So with, let's say, 20, 30 years down the line with quantum computing, the game changes completely. So, sort of one of those things that the claim which is made very emphatically today may not necessarily be tomorrow with.
Absolutely.
Yeah, so just wanted to put that also in
Yeah,
perspective.
and in fact, it's an aspect I'll touch upon even later in this talk. Yes. So we will in fact coincidentally be talking about this a little bit later down the line. Any other questions? Okay, so let's keep going. Okay, so functionality and security. Now let's start looking a little bit more deeply at, you know, the cooking that I promised you we'll do together. So functionality, I want to say, requires some mathematical structure, okay, and security requires some hardness. So let me try to go deeper into this. Now I'm trying to build an encryption scheme, okay. I need to use some mathematical structure. So now I'm thinking of my message as some sequence of bits, let us say, and I want to hide these. So there is some mathematical structure using which, you know, I have to construct this scheme, and I need two kind of conflicting properties. One is that there should be some nice behavior in this mathematical structure. We'll see examples, which allows there to exist a secret key which will enable decryption, right? So there has to be some structure there, okay? On the other hand, there should be some computational hardness or algorithmic hardness, so that if you don't have this secret, then, you know, this problem looks hard to solve. So we'll see examples of this, right? Now, like I told you, we have these two conflicting requirements, and we'd like to get these both together from a suitable hard problem in mathematics, okay, or computer science. So typically when we think of a source of hard problems, we think of complexity theory, right? So NP complete problems, NP hard problems, and so on. So are these, are these going to really give us the right properties that we want? Okay, so the question I'd like to ask is, where can I find these suitable hard problems? Any ideas?
Natures or symmetric.
What?
Mathematical natures or symmetric, like flowers, like in plants.
Sure. So maybe for now, let's restrict attention to, you know, these computer science complexity theory classes, right? So here we would hope to assume something that is widely believed, something like P is not equal to NP or something like that, right? And we'd like to build cryptography from it. So cryptography is going to prove to us that breaking some encryption scheme is at least as hard as solving some mathematical problem. Okay, and yeah, sorry, the fonts are getting messed up, but this mathematical problem, we can only conjecture that this problem is hard. Okay, now this sounds like a problem, right? Because it seems like I'm basing my security on a conjecture, and indeed it is sort of an uneasy place to be, but, you know, we have to conjecture something. At the very least, we need to conjecture that P is not equal to NP, right? And is this enough? So is it enough for me to believe that P is not equal to NP? Does this give me cryptography? And it turns out that not quite. So there are many worlds, okay, that possibly we might live in, and these were defined by Russell Impagliazzo. Let's look at them, okay. So what is the first world? The first world is called algorithmica. So in this, P is equal to NP. Now note that even though we believe that these are different, we actually don't know, right? So if P is equal to NP, then, you know, we cannot do cryptography. Then there's heuristica, which says that P is not equal to NP, but finding hard problems is hard. So there exist hard problems, okay, from which I can build cryptography, but finding them is hard. Then there's pestilent, which says that there exist problems that are hard and I can also find them, but there is no asymmetry of computation. Okay, so this is sort of formalized by saying there are no one-way functions. Now, one-way functions are the most basic primitive of cryptography. What is a one-way function? It's a function which is easy to compute but hard to invert. Okay, so now what would I like? I would like there to be not only a problem which is hard, but there should be some asymmetry, which means that it should be easy to compute in one direction and hard to compute in the other direction. Okay, so this is a one-way function. Then there is another world which is defined, which is called mini-crypt, in which one-way functions exist. If you take a course in cryptography, you'll see that this implies the existence of symmetric key cryptography. And then there is an even more brave world, which is cryptomania, in which we conjecture that public key encryption exists. Now, why am I showing you these different worlds? Because first of all, they capture the state of our knowledge. We don't know, right? We don't know which of these worlds we live in, right? So that's what we're asking here. Which world do we live in? And the answer is that actually we have no idea. Yes?
Alright, so for cryptomania, I would like to understand if there is a more complexity theoretic like definition, or is the definition tautological, that PK exists and that's cryptomania?
Yeah, it's the latter. So, we're just saying that a world in which PKE exists, we call it cryptomania. These are not mathematical terms, so thanks for asking this. These are sort of just, they just capture, what we believe exists. Okay, so if P is equal to NP, there is no cryptography, right? And then it's not enough to just assume that P is not equal to NP. It could be that the two are different, but it is still hard for me to find hard problems with which to do cryptography. It could be that I can find them, but I don't know how to use them because there's no one-way function. So there are different possibilities, and we're just loosely defining these as these, okay? So we don't know, okay, but we want to hide our information. So we are going to conjecture that we live in cryptomania. Okay, so we will build cryptography assuming that certain problems, are hard in a way that allows us to build crypto. Are there any questions? Yes? So I wouldn't, they are stronger, yeah. So, they are stronger and stronger assumptions. Any other questions? Yes?
Ma'am, what does it mean that finding hard problem is find? Hard means exponentially, which takes
For
exponential
example,
time.
yeah, you could think of an exponentially hard problem. Like, let's take an example, like, maybe I think, so let's take an NP hard problem, okay? Like, let's say the traveling salesperson problem or something like that. Now, is it easy for me to find an instance of a graph where this problem is hard? We know it is hard in the worst case. But can I find an instance efficiently where I know this problem is hard? This is what I mean. Okay? So we are going to make conjectures about, problems that we can actually sample from. Like, we can find problems that we believe that this problem is hard. I mean, this instance of the problem is hard. Okay? Does that answer your question?
So we know that the problem is hard, but the given instance is hard or not is the question.
Yes.
Okay.
Very good question.
So, here, if we know that one-way functions exist,
We don't know.
no,
by
I
the
mean,
way.
so is
if
the
we
problem
assume,
that,
if we assume, yeah.
so do we know that we can invert the function?
The assumption is that it is hard to invert.
But, I mean, a solution exists. That is not a problem.
Yeah, a solution exists. Okay, so back to encryption. Okay, so now, I want us in this lecture to actually build an encryption scheme. Okay, so let's do that. So, this is where we were. We want to have some problem which, allows me to get both correctness and security. And here is a candidate which we actually use. Okay, so this is called the closest vector problem on lattices. This is what a lattice looks like. Okay, so this is a simple two-dimensional lattice. Just think of it as a periodic arrangement of points. And the question that we are asking here is that if I give you some arbitrary point in space, okay, so some point t, can I find which is the closest lattice point to this point? This is the question. Okay, is it clear? So this lattice is our mathematical structure that I was talking about. So now we are getting more warmed up, so more concrete examples. So this is my mathematical structure. So it's a periodic arrangement of points, and I represent it using some basis vectors. So most of us are used to these basis vectors, right? So I have these basis vectors here, just 2, and I take integer linear combinations of them. Okay, so this is a discrete space. And all these integer linear combinations, like if I take b1 plus b2, b1 plus 2b2 and so on, I get points, right? And these will be arranged in this nice way. And the question I am asking is that, if I give you some arbitrary point in space, some t, which is my closest lattice point? Okay, so this is the question. Okay, so you see like this little circle here, yeah. So here is my point t, and I am trying to find within this circle is there like a lattice point. This is my problem. And a little bit more formally, a lattice, as I already told you, so it's a set of points with a periodic arrangement. The simplest lattice you can think of is just the integer lattice. And in these slides we are only looking at two-dimensional lattices. But when we work with them, we will actually look at multi-dimensional, okay, so hundreds of dimensions, okay. So this is a simple lattice, and I can apply a linear transformation via some matrix B, let us say, and I can get another lattice, okay. And this B is going to be like my basis matrix. So it's the basis vectors of my lattice. I will take integer linear combinations of them and get the whole lattice. Okay, so yeah, it's a discrete subgroup of Rn. This is actually a nice mathematical definition. And this is my closest vector problem. I already told you what this problem is, right? This is a little bit more formally. So mu is some parameter I give you. Okay, so I want you to find me a point, a lattice point within some distance mu. Okay, this is the question. Now this problem is a very hard problem, and when I say hard, actually the efficiency of solving this problem is exponential in the dimension of the lattice. So this is why I need high dimensions, and I also want to say that the decision version of this problem is also hard. So what I showed you is a search version, that I give you t and I am asking you to find some closed lattice point. A decision version will be, I give you a point and I ask you, is this close to the lattice or far from the lattice? Okay. So there can be like some measure of that. Like if I am within this distance, mu, let us say, then I am close to the lattice, otherwise I am far. Okay. So this is the problem that we'll use. So now, I gave you a problem which I told you is hard, okay. Now, how do we know it's hard? So actually the version of it that we'll use in cryptography is an approximate version, and really speaking, we only conjecture that this is hard because, we've studied it for decades. We don't know. Lattices actually have been studied for hundreds of years. In computer science, they've been studied for decades. And we don't know of better algorithms. So cryptography is also like a sort of a, trying to make the best of what we have. Like in algorithms, we want to solve problems, right? We want to do it efficiently. Most of the times we cannot, right? And when we cannot, we can hope to at least do something useful with it, like cryptography. Okay? So this is our hard problem. So remember, we were saying there should be functionality and security, right? And for security, we need some problem to be hard. But I also need functionality, right? So I need some mathematical structure which enables me to get functionality. Okay, so where am I going to get this structure, or where am I going to get my correctness from? So here we'll introduce this really cool notion of trapdoor functions. Okay, so what's a trapdoor function? So let's generate some function f and a trapdoor t. What are these objects? So this function is, you know, some function going from some domain D to some range R. Okay, and this is a one-way function. So what does that mean? I have this domain range, right? I have some point x in the domain. I apply this function. I get to some point in the range. And as I already told you, I mean, if I give you x, I can compute f of x, which is y. I can do this efficiently. If I give you y, I don't know how to go back to x. Okay? This is one-wayness. And what a trapdoor function lets you do is it lets you invert given this trapdoor. Is the concept making sense? Okay, so in general, I don't know how to invert this function, but I want to give you some secret information that lets you invert it. Now maybe you're thinking, you know, we're just reducing the problem to another problem, which is sort of true, but I'll show you how to build these trapdoors. Are there any questions? Okay, so fine. So I showed you a lattice, right? I showed you a hard problem on a lattice, and I told you that we're going to use trapdoors in order to get, you know, the correctness of our encryption scheme. We're building it now, okay? So let me first show you what these trapdoors can look like, and this is just going to be like a construction by picture. So this is my two-dimensional lattice, okay? This is one basis of this lattice, this is another one. There can be many different bases, and depending on the basis I have, you know, just by eyeballing it, you can see that I can, you know, divide the space into these parallelopipeds, right? So I can just kind of chop up space around the lattice points, you know, parallel to the basis vectors, and I get these parallelopipeds. And different bases will give me different parallelopipeds. Okay, so far so good. Now I'm going to introduce this notion of a good basis. So what do, all this can be made mathematically rigorous, but just for the sake of intuition, okay, what is a good basis? It's a basis which is, you know, quite short, hand waving here, but quite short and almost orthogonal. Okay, we'll see why we like these bases. So if I have a basis which, you know, is fairly short and quite, and, you know, fairly orthogonal, this can be mathematically you would want like the Gram-Schmidt norm of the basis to be bounded in some way, but this is the right intuition. Then I'm going to call it good. And you know, if I have this good basis and I ask this question about the closest vector, right? So I give you an arbitrary point in space and I'm asking you what's my closest lattice point, right? Then it turns out that I can actually solve this problem. So, you know, the way that we do this, given any basis, okay, what I can do is that I can always output the center of the parallelopiped that contains T. Okay. So I have my basis, right? I have these parallelopipeds and I am giving you an arbitrary point somewhere and I am asking you which is my closest lattice point. Now, for any basis, it is possible for me to find the center of the parallelopiped in which this point T lives. This is true not only for a good basis, but for any basis. I can always do this. But if my basis is good, right, then this answer will be pretty good. Okay, whereas if my basis is bad like this, right, then I am going to output, so this is my parallelopiped, right. This is the center of the parallelopiped that contains this point T, and I am going to output this as my closest lattice point. But you can see just again, just by eyeballing, that this point is closer, this point is also closer than this point. Okay. So again, this can be made rigorous, but when I have a bad basis and I output the center of the parallelopiped that contains my desired point, then this turns out to be off by a large margin. Whereas if I have a good basis, then I can solve this, you know, fairly well. Okay, so this is an asymmetry that we have. Okay, so
Hitting the basis, is that?
sorry.
No, it seems like the intuition is about a floor function which will capture it.
It's, I think you may have the right intuition. More than floor, it's like a rounding.
Yeah.
So it could be, yeah. So what you can do is, I mean, I have some point, right? And I can just try to express it in the basis and round off the difference. This will sort of give me the center.
Okay.
Yeah.
So if it's a good basis, then it's
Exactly,
perfect,
yeah, exactly. So now the closest vector problem that we saw, as well as other problems, they are hard if I give you an arbitrary basis. Okay, but if I give you a good quality basis, then actually I can solve these problems. And this is the asymmetry that we will use in building our encryption scheme. Okay, so we are going to use our short basis as a cryptographic trapdoor. Okay, and now I claim that we have everything we need to build our first public key encryption scheme. So we have a lattice, right? This is our mathematical structure. It has some nice structure. It's this additive structure. We saw a trapdoor on this. Okay, so what did we see? Just to recap, we saw that if I give you an arbitrary or, you know, some bad basis for this lattice, then solving this closest vector problem is hard. If I give you a good basis, then solving this is easy, right? And recovering the good basis from the bad basis is hard. Okay, and in the absence of the good basis, I don't know how to solve this problem. So that is our hardness. Now I'd like us to design a public key encryption scheme using this.
Yeah, like how will we know that the basis given is a good basis? Like, is there any boundary that under which?
Yes. So like I said, we can make it rigorous. So, you know, there will be some property that it satisfies. So in a public key encryption scheme, we have a setup algorithm which will generate the public and the secret key. Now who can guess what should be the public key and what should be the secret key here? What should be our public key? What?
The lattice parameters could be the public key and the basis could be the private.
So there are which bases?
I mean the good basis should ideally
Good.
be the
So
private.
good. So you know that's right on track. I mean if something is, you know, letting me do cool things, solving hard problems, it should be kept secret. So our good basis will be our secret key. Our public key can be a bad basis. Okay, not just lattice parameters, but actually a bad basis, because I also need to do stuff publicly. So my, you know, my key generation or setup will give me a good and a bad basis, let us say, okay, and I'll keep the good basis secret, I'll publish the bad basis. Now you have to encrypt something, okay. Now for simplicity, let's try to just encrypt a single bit, a 0 or a 1. I want to encrypt either a 0 or a 1, and I need to do this using my bad basis. How should I do it? The intuition is that the attacker, in the absence of the good basis, should not be able to tell if it is a 0 or a 1. The two should look the same. So the encryption of 0 should look similar to the encryption of 1. So this is where the hardness of our problem, the hardness of CVP should come in, right? So can you guess how would I encrypt? What is hard? What did we say is hard? Finding the closest lattice vector is hard. Even distinguishing whether I am close or far to the lattice is hard. Can we think of how could we use this to encrypt a bit? Any thoughts?
Find the closeness as 0, find the further awayness as 1.
Okay, so let me reinterpret what you said. I think what you are trying to say is that 0 should be somehow close and 1 should be somehow far. That's exactly the right intuition. And why do we get that intuition? Because it's hard to distinguish close from far, right? And I want it to be hard to distinguish 0 from 1. So let me encode 0 by, you know, close and 1 by far, for instance, right? And now how will I decrypt? Anyone else? So I have my secret basis, right, as the secret key. And what can this do? It can figure out, right, is my point close or far. So that's it. That's our first public key encryption scheme. So we'll make the bad basis public. We'll make the good basis secret. Okay, to encrypt, we'll use the bad basis. For 0, we'll output a point which is close to the lattice. So using a bad basis also we can do this. How? Take the bad basis, you know, just take some linear combination, get a lattice point and just shift it a little bit. Okay. It's easy even using a bad basis to output some lattice point, right? Bx for any integer x is a lattice point. And now I'll just shift it a little bit. I'll just add a little bit of noise to it, perturb it a little bit. This gives me a point which is close. What gives me a point which is far? Perturb it by much more, for example. So this is the way in which.
Can we reinterpret as like x-axis, y-axis as zeros and ones, and more bits, more computation is there. Then if we go into multi-dimensional version of the vector space, then the point can be easily found out. So it also
Actually,
shows that the cryptography is 100% possible at that point. At that point when we go multi-dimensional.
Actually no. So I don't think that's the right intuition. So the axes really don't have anything to do with 0 or 1. 0 or 1 is being encoded.
No, we compare it with hardware, like we compare that algorithm because we are mapping our algorithm into cryptography by hard and something, like hard problem and not hard problem. So if we map that problem as a some hardware system computation, then we can say that. Can we say like that?
In my judgment, no, we cannot. Okay, but we can talk more offline to make sure that I understand what you're saying. I don't think such a mapping is really possible. Okay. Any other questions? Okay, so yeah, as I already said, in order to decrypt, we use T to figure out whether it's close or far. And the security comes from the hardness of the closest vector problem, and the correctness comes from the properties of the good basis that we saw. Are there any questions? Yes?
Why is it hard to go from one basis to another?
Because we don't know how to do it.
Okay, so it's not easy, or it's just not something we can do. So how do we generate
There
the
is,
basis?
so in cryptography, in fact in computer science, I mean we cannot disambiguate hard and don't know how to do it.
Okay.
We don't know how to do it, therefore we conjecture it is hard. So this closest vector problem has been studied very, very thoroughly. It's one of the problems which actually solving it exactly is even NP hard. But as I said earlier, you know, NP hardness, we don't know how to use it. We need something which is average case hard, which means that if I sample a random lattice, right, CVP should be hard on that lattice which I sampled. Otherwise, if there exists a lattice which you know has CVP hard, I don't know how to use that, right. So because we built this encryption scheme, for this I need the B, I need the T, right, I need to construct them. So we need average case hardness, and we are going to actually use like an approximate version of the closest vector problem which is not NP hard. So actually getting cryptography from NP hardness is one of the outstanding open questions in the field of cryptography. We don't know how to do it. Okay. So we will use a version of the problem which is not NP hard, but which we don't know how to solve. And when we say we don't know, I mean this is a very educated we don't know. It's not just looking at it for 2 minutes and saying we don't know. It's been studied over decades and we don't know. The community, the global scientific community does not know after several decades of rigorous study. So we believe that, let us say that, fine, let us say that our conjecture is even false. We at least don't expect the attacker to figure this out in time to break it. You see, so that's why I said it's like a chess game. We don't actually know. You know, we guess, we believe, we conjecture that this problem is hard, and we prove that in order to break this encryption scheme, you will need to solve the closest vector problem, right? And we expect that the attacker cannot solve this problem. Does that answer your question?
Yeah, no, okay. So if you have a lattice, finding a good basis and a bad basis is doable.
Yes. So sampling a lattice together with a good basis is doable, yes. But given a particular lattice, finding, and this is intuitive, right? I mean, I can sample short vectors which are nearly orthogonal, take integer linear combinations of those and that define that to be my lattice. So this is actually where, you know, when we saw the many worlds, right? So this is a way of sort of sampling a problem with a solution. You see, so I can find, I mean, I first pick the solution and then I build the problem. Okay, so this is not, this is doable, this is not hard. But if I fix the lattice, right, and I ask you to find this short basis, then I am basically reduced to trying all possible combinations of short vectors, and this will take me exponential time. Is this clear to everybody? Yeah.
Using the bad basis, like when we discussed bad basis, we said that it is possible that the answers that it would give would not be accurate. So if we are
No. We said that it is not possible. The word possible is not the one that we used. We said it is highly unlikely that the answer to the closest vector problem that the bad basis gives you is a good answer, right? But note that in encryption, we are actually not solving any hard problem at all. We are creating an instance for somebody to solve. Do you see that?
Right, yeah. So like my question was just that is it possible that if we use a very arbitrary basis, could it be so bad that we actually end up outputting the opposite, like we end up encrypting 0 as a...
No, this is what I am trying to say, that I'll finish whenever. How much time do I have?
So we started 5 minutes late. So
Yeah,
let's
yeah.
with another talk after this.
Yeah.
Have a nice lunch break, and please don't just sit among yourselves. Please sit with the speakers, your faculty, and please talk your heart out during the lunch time.
Yeah, so Varsha, I'll finish within 5 minutes, okay? So actually this is only part 1 of the talk, I'll just skip the second part. So this was the warm up, and then I was going to show some advanced crypto, like something we worked on. We'll just skip that altogether. So what I wanted to say is that let's be very careful, okay, about where these bases are being used. So previously what we said was that using the bad basis, it is hard for me to solve this CVP. What does that mean? Using the bad basis, it's hard for me to decrypt, which is what I want. Using the public key, it's hard for me to decrypt. This is perfectly what I want. Using the bad basis, it is very easy for me to encrypt. Note the difference, right? This is the fundamental asymmetry that we are playing with. Why is it easy? So I told you that, you know, just integer linear combinations of the basis vectors, whether good, whether bad. If you go back to, you know, the slides, right, like any of these slides, right. So, these are these basis vectors, right. If I just add them with each other, right, I get points in the lattice. So, does everyone agree with me that I can generate points in the lattice irrespective of the quality of my basis? Just take integer combinations, right, you will get some point. Now, I can push it away from the lattice. How? Just perturb it, add some noise to it, just push it away. This is easy, right. So, pushing it a bit away or quite a bit away, this is easy. So, encryption always works. Okay, and so it is not that because the bad basis is bad, it is also bad for encryption. The beauty is that it is good for what it needs to be good for, and it is bad for what it needs to be bad for, because of the asymmetry between encryption and decryption. Encryption is about creating a bad problem. Everyone knows to do that in life, no? Solving hard problems is hard. Creating problems everyone can do, right? So, I will just conclude here. Okay, so I just wanted to say that so all of cryptography is this sort of jugalbandi between correctness and security, algorithms and complexity, structure and randomness. Okay, and it has lots and lots of open problems. It is at the very heart of the science of computing. As I already told you, we do not know how to use NP complete problems for cryptography. We do not really know how hard are the problems that we do know how to use, and this is something that my advisor told me when I was a PhD student. Cryptographers rarely sleep well, and really this is true. Okay, I do not know, I am supposed to be selling this field to you, but really, I mean, you do not know anything. Okay, so you do not sleep well, but okay, and if this weren't bad enough, so again some more reverse advertisement here. Okay, so quantum enters the picture. These are computers that use quantum rather than classical physics, and they break all number theoretic cryptography. Okay, so I am going to skip all this, and I will just say that in summary, okay, so cryptography is powerful, cryptography is surprising. I did not want to skip these slides, right. So, but most importantly, cryptography is beautiful, okay, and I hope you will join us in this wonderful adventure. Thank you very much.
Thank you, Professor Agrawal, for such an interesting talk. I hope it's inspired you all to explore the amazing yet paradoxical world of cryptography. We would now like to express our gratitude to Professor Shweta Agrawal with a token of appreciation. I'd like to request Professor Sharad to do the honors. Thank you, ma'am. Thank you so much. In the words of Grace Hopper, a famous computer scientist, the most damaging phrase in the English language is, "It's always been done that way." RISC is our way to show our commitment to challenge the status quo and push beyond the limits of convention. With these words, we will transition to our next speaker. I am pleased to introduce an esteemed member of our faculty, Professor Swaprabha Nath. Professor Nath is an assistant professor at the Department of CSE here at IIT Bombay. His research lies at the intersection of economics and computation, with applications spanning social and industrial paradigms. His work has been published in top AI and multi-agent systems conferences. His accolades include Fulbright Nehru postdoctoral grant, TCS PhD fellowship, and the Honorable Mention Award of Yahoo Key Scientific Challenges Program. So today he will be talking about multi-agent AI from a game theoretic viewpoint and show how robust AI systems can be built with such agent. So let's welcome Professor Swaprabha Nath on the stage.
so now I should be. Okay, so thanks for the great introduction and welcome you all. So this talk is going to be about artificial intelligence, which I think everybody is really very excited about. But with a small caveat that there is this multi-agent thing, and I'll give you examples and try to motivate why this multi-agent part is important. So I am Saprava, I'm a faculty here. So the moment you think about artificial intelligence, what comes to your mind? Some random guesses? ChatGPT, great. Large language models, auto correction when you type in, grammatical corrections, then detection of faces and all those things. Now, if you have already known that area well, then you must have known that behind every artificial intelligence technique, there is an optimization problem that is running behind. So be it deep learning training, your deep learning is an optimization problem, and several other things which are all optimization problem. I will try to call that as a single agent problem. Why? Because you are given a bunch of data and you are trying to learn something from it, and in some sense you are solving the optimal solution for yourself or maybe the person who is trying to learn. How is multi-agent systems different from them? So let me start with an example, and it's a very toy example. Don't take it too much to your heart, but this is how to introduce it. So imagine one kingdom. Here is the king and the queen, so the queendom. And both of them are modern kings and queens, so they have artificial intelligence at their hand, and they can design systems, so they can use AI for two different purposes: to develop better agricultural techniques, so maybe something to do, how to do a hybrid type of a crop or something else, or they can use AI for more not so nice things like warfare, developing guns or weaponry, aircrafts, so that you can actually attack the other nation and essentially try to capture that nation. Now, in this diagram, so you can see, and let's imagine, I mean, AI is definitely expensive and also time consuming, so you cannot really invest your resources and effort on both of them, both agriculture and war. So for simplicity, let us assume you can only spend on either agriculture completely or on warfare completely. No mixing is possible. Now the numbers, so I'll place some numbers in these boxes, and that is, you can imagine that how much amount of happiness, satisfaction, or let's say profit that they are going to get if these two individuals choose that pair of actions, right? So remember, there is a slight difference from the other type of AI problems that we discussed about. Here, the outcome depends on the pair of choices or the combination of the choices that all the players, so in this case 2 players, the pair of choices that they make, that gives out an outcome. So imagine if both of them had chosen agriculture or used AI for agriculture, both of them could have developed, they could have solved their food security issues, and then they get some amount of happiness, which I'm just quantifying by this number 5. The actual units or the numbers are immaterial. All that matters is how they compare with the other numbers. Now, if both of them go for warfare, of course, you can imagine that they will engage in conflict. So I have deliberately chosen the numbers smaller because now there will be a lot of destruction and other things. So your happiness or your profit will not be as high as if both of them chosen agriculture. A vastly interesting thing happens, a very curious thing happens when one of them chooses agriculture, the other chooses war. So for instance, in this case, I mean, these are symmetric cases. Why these numbers? Because if, let's say, the king chooses agriculture and the queen chooses war, then the warfare, so because king has spent no energy or effort in warfare, they won't be able to defend their own country. So with warfare, the queendom will actually rule over and essentially take care of all the agricultural produce that they have made. In addition, they will have additional land and maybe prisoners, etc. Okay, so so they will have more happiness. So of course, on top of 5 that they have produced, they will also have something more. And the kingdom loses everything. They have lost their own maybe life and some land and all agricultural produce, everything. And the symmetric opposite thing happens here. Now, imagine you are the queen, and which of this agriculture or war choices would you have made? Just give a second, give a minute of thought, and think about what should have happened, you should have done if you are in the position of the queen. Assuming that you have no communication and no communication with the other country, and even if you communicate, then also there is a chance that the other country will not actually listen to you, or certain contracts will not be feasible to satisfy here. So what should you have done? How many are in favor of agriculture? Okay. Okay, so few very highly optimistic person. Okay, so how many are in favor of war? Very good. Okay, so I don't need to take this lecture. Okay, so the reason here is the following. So yeah, so this is the problem, and the decisions have to be simultaneous because this is happening for a long period of time, right? So investing in agriculture or warfare takes a little bit of time, and you cannot suddenly switch between one from the other. So if you have already invested, you have to stay with that, let's say, for a year or so, right? So imagine the situation of the king, the queen. If the king chooses agriculture, what are the options that the queen has? So between agriculture and warfare, you can see. So okay, so I did not explain what these numbers mean. So this tuple, you can see that each of these numbers, the first number corresponds to the happiness of the queen. The second one is the happiness of the king, right? So everywhere that's the meaning of the number. So if you look at the happiness, so the first entry in that tuple is the happiness of the queen. So therefore, if you look at the situation where the king has chosen agriculture, the optimistic people who are sitting there, so if they're choosing agriculture, the queen should actually choose war because that's giving him more happiness, more utility. And here we are assuming, yeah.
Is this table known by both?
Yes, the table is known. This is publicly known. The numbers are publicly known.
What the other side is doing?
Doing is not known. They are trying to take this decision simultaneously. Yeah, so here we are assuming that everybody is self-interested. They only care about their kingdom or queendom, does not care anything about the other one. So that brings us to the warfare. Now, if you do the same thing, you apply the same logic on warfare, it's better to defend your country rather than getting ruled over by somebody else, right? So again, war turns out to be the outcome. So those majority of you who are actually warmongers, they were actually right. And like it or not, that's the prediction that we can give. In a situation where people are completely competitive amongst each other, the war, war, so we call this the strategy or the action war as a dominant strategy. The reason for saying that is that no matter whatever the other person is doing, it's still better to pick that strategy over the other one.
What is the cost function with the sum total of the happiness of both kingdoms?
The equilibrium would have changed. Equilibrium would have changed, certainly. Yeah, so these numbers I have chosen carefully. If the numbers were different, then yes, you can see that the equilibrium, the conclusion that I am making would have been different. But yeah, so here I am just trying to motivate one special situation where what is collectively optimistic is not the equilibrium outcome. And that is, okay, so we call this war, this strategy profile of war, war as the dominant strategy equilibrium. The first time that we are using this word equilibrium, and this is where the multi-agent part comes in. In multi-agent systems, we do not really talk about optimal solutions because there is no optimal solution here. If you say that agriculture, agriculture is an optimal solution, yes, they are collectively optimal, but they are not an equilibrium. So equilibrium is this war, war, And therefore, in a multi-agent scenario, we will shift our notion from being that of an optimal solution to an equilibrium solution. So that's the first diversion that happens here. And one can see that the collectively based outcome is actually the optimistic solution, both being agriculture. And that essentially changes when you look at the self-interested agents. Now, so taking an inverse view of this, that how we actually design systems, if we want this agriculture, agriculture to be an outcome, or the equilibrium outcome, that is exactly what we are heading towards. Okay, so let me give you few more examples, essentially to actually motivate this whole question. Okay, so adding resources blindly does not improve the society. How? So this example fits very well with the IIT Bombay campus. So let's say A is the location where all the hostel blocks are, and D is the location of all the lecture halls. And each morning, the students need to reach to their destination, their lecture halls for their lectures. And there are two possible paths, one via B, one via C. And these paths have certain things. Okay, so let's say for simplicity, I assume 100 students. Each of them have a vehicle, a bicycle, and they can bicycle through this path in two different ways. And there are characteristics, special characteristics of each of these roads. So this path, this road A to C and B to D are wide highways, maybe the larger ones where it does not really matter how many bicycles are moving there. It always takes 600 seconds just to go from A to C. Similarly from B to D. A to B and C to D are congested lanes, and if the number of vehicles increase, then it actually increases your travel time. So one vehicle going there takes 5 seconds, two vehicles 10 seconds, and so on. Right? So N2 is the number of vehicles that is traveling on these roads. Now, let's ask this question. So if you are the vehicle, one of those students who are riding a bicycle, which path should you have taken? Given that there are other people, everybody is trying to minimize the time to reach to their destination. Flip a coin, okay, so the first individual, okay, just flip a coin and go one of them. Now, suppose the moment you have started taking your bicycle, you have seen that someone is taking this other path, let's say ABD path. What should you do to minimize? You take the other path, right? So you don't conflict. The third one, again flip a coin. Fourth one takes the path which the previous person did not take, right? So in some sense, you are splitting this thing, and you can see that why this is an equilibrium the way we have defined it before. So when we have this original circuit, original path, so you can imagine the 50 vehicles will go on each of these paths, right? So what will be the total the time taken by each of these vehicles? 600 plus 50 vehicles going here, 850. Okay, so 850 seconds for each of these vehicles. Okay, so now the IITB administration has decided we will have a teletransporter device. So the moment you are in B, you are in C. Okay, so this is a one-way traffic. So suppose I have a kind of a shortcut route which takes negligible time corresponding to all these other times. Now, can you tell me the same answer? What would be your choices now? The first one will take which path? A to B and then C, D, right? So yeah, so that will take just 5 plus 5. The second one? Second one will also take the same path. Why? So the second one, if takes this ABCD path takes, so now there are two individuals, so 10 plus 10, which is much smaller than 600 plus anything, right? So this is a one-way path. You cannot go the other way. So is everyone convinced that the second person will also take the ABCD path? Yes. What is N1 and N2? So N1 is the number of vehicles which are traveling in that path. So that's what we are trying to find out, right? So let's say I'm starting with the first vehicle who is taking that path, so then it's just 5 seconds at that point. The second one is thinking about, so at this point, everybody is thinking about whether to take that path. Yeah, so N2 is the number of vehicles on this path, so what will happen? So, yeah, go ahead.
Does the person at A know how many vehicles are between CD while he's at A?
Not at this point, but given that you can, right, I mean, even if you do not know that, you can at least see the path between A to B, right? Still, you should be choosing AB, right? Because, okay, so imagine the situation where 99 people are going through this path AB, and you know this. You have just seen all the 99 people have gone before you. Would you ever take AC? Because 99 times 5 will still be smaller than 600. So you will never take this AC path, no matter whatever happens after B, right? So is that example clear to everyone? So what will be the final equilibrium outcome in this case? Everybody will take this ABCD path. Now calculate the time for that. Now 1000. Okay? So actually it's a bad design, right? So adding resources blindly does not improve your society. So this is one example. When you have multiple self-interested individuals, all of which are trying to minimize their time to reach the destination, you should choose this design of this teletransporting device in some place where you actually help the people and not reduce their time of traveling. So B, D, and AC are not used at all. Those resources are not used. And these are not toy examples. There are real-world examples where people had to break down a newly built bridge just to take care of the congestion. Okay, so design is important. That's what I want to drive home. Now, the question is, how do we design a better society? And that is exactly the other part of this talk, which is to design. So far we have given predictive guarantees. Now we are going to give prescriptive guarantees. And here, for simplicity, I'm assuming that there is a cake that we need to divide. And you can imagine that this type of, instead of a cake, you can think of resources, spectrum resources, or any kind of divisible resources. And you want to do a fair allocation or fair division of this. What is assumed for this resource is that they are heterogeneous, which means that the equal amount, so if I cut a piece here and cut the same sized piece somewhere else, because maybe this piece has some cherries on top of it, or it has more chocolate and you like chocolate, that piece has a different value, different happiness for you than something which does not have them, right? So it may always happen, right? So you cut the same sized piece, but you like one piece over the other. So that is heterogeneity in the resource. It is perfectly divisible. You can cut it in whatever way you want. And the preferences are differing. That is, the same cut piece of chocolate, I might not like chocolate that much, and you may be a fan of chocolate. So that piece is highly valuable for you and very less valuable for me, right? So this is a differing preferences across different individuals. Now, for simplicity, what we typically do is imagine this cake as a real line interval to make things simple, line between 0 and 1. And your valuation is like a distribution over this 0 and 1, right? And different people may have different valuations. The size of the piece that you get, you just integrate over your valuation of that piece, and that is your total value for that piece. And what is now, and we are also going to use the normalization, that the total value for the entire cake, if you get the entire cake, that is valued 1. That is the normalization. Now, we have not defined what is a fair division here. So one can say that a fair division is where you get your piece, which is at least more than the average. So you are satisfied because at least you got an average share, more than the average share. There is another notion of fairness, which is called the envy-freeness. So imagine somebody envies. So suppose there are two kids, and the mother tries to cut this cake on the birthday, and one person gets a piece and complains that the other kid got a larger piece, or I like his or her piece more than my own piece. Then there is a situation of envy, and I want to ensure that that never happens. That is, everybody is at least as much happy as he or she would have got the other piece, right? So the value for So here a little bit of notation, the value that you get for your own allocation, that is AI, is at least as much as your own valuation for the other piece, some other j. And this, if you can ensure for every agent, then you can say that this is a envy-free allocation. So for the simple example of 1 cake and 2 kids, can you come up with, I'm sure that, how many of you have siblings? So you have encountered this problem at home at some point of your life. So how did you solve this, or how your mother or father solved this problem? Exactly. So yeah, so I'm just going to call, so essentially the answer that was given is essentially a solution for the 2-agent problem. I call it a I cut, you choose algorithm. So the mother says that one of you cut this piece, the cake, and the other person gets to choose first. And why does this algorithm work? So let's see why this, so my first question, is this proportional? How many thinks no? Why?
Because they are both trying to optimize for themselves. The person who will cut will try to do it such that no matter which one he gets, he'll be happier. But the person who choose will definitely try to go towards the envy-free direction, where he'll try to choose the one which he values more.
So the first individual who is cutting exactly in half according to his view, right?
Yeah.
So
that is proportional.
That is proportional for him. And the other person gets, if there is a larger piece, he gets at least half of that, half of the entire cake, right? So the argument that you gave is actually proportional, right? So this is the same argument for proportional. So yeah, so imagine the situation that someone, so here you know that when you are cutting the cake, you are not going to pick the first piece. So if you cut it unequally, there is a chance that the larger piece will go to the other kid, right? So you will cut it exactly in half according to your view. So if you like the cherry, maybe you will also cut the cherry in half. So you are equally happy with any piece. So that satisfies this proportionality constraint for player 1, the first player. And the second player gets to choose. So if she feels that there is a larger piece, then according to her view, she will pick that, and she will be at least half happy, right? Okay, so is it envy-free? So use the same logic, you are cutting it exactly in half. So you are indifferent between these two pieces. No matter whether your sibling gets the other piece or you get this piece, doesn't matter. You are indifferent, you do not envy this part, any of these pieces. So player 1 is indifferent between these two. The other player does not envy because he or she picks first, right? So the piece that she picks is at least as much as the other piece. That's why she has picked it, right? Okay, so this actually satisfies both these conditions, both this proportional fairness. So yeah, so this is an animation of showing how, so it might not be the physical half because these are valued half, right? So maybe this half, this part is half because you like chocolate and the whole chocolate portion is on this part. And something else which is not very valuable for you, okay? So it is proportional and it is also envy-free. I don't really have time to explain so this is for cases where actually you have a divisible resource, but you can actually extend these ideas for indivisible objects as well, and let me just skip that. So that's where we are. So with these examples, I hope that I am able to communicate to you that a game, the way we define game in game theory, is an interaction between multiple agents, all of which are trying to maximize their own happiness. In this terminology, we'll be using the term utility. And the game theory part, that is the first part where we were trying to predict what will happen in that game, is predicting the outcome of the game. And therefore, it's a predictive approach. And in the later parts where we are trying to design, let's say, how to cut this cake in a fair way, that is falling under this paradigm of mechanism design, where we are trying to give a prescription how you should design this algorithm such that certain good things happen, fairness happens, many other things happen. And the applications, so these are toy examples, but the applications are many. So in the mechanism design, you will see this Google, Facebook. The moment you search for something, you get certain types of ads. Maybe you have purchased a ticket for a destination. The very next time you see different ads on different pages is about the destination of booking hotels in your destination place. How did they know it? Because you have, while booking, you have given your Google email address, and that email has come, so they are processing it and gathering the information that you have actually purchased a ticket, let's say to Goa, and they start showing you ads, hotels in Goa, tours and travels in Goa, and so on, right? So those online advertising, so what happens behind the hood is there are certain advertisers, the hotel owners or the travel owners, they pay Google the moment you click on one of those ads. And they want to show, they are essentially trying to buy your eyeballs. And that is exactly how this online advertising works. The other brilliant application is stable matching. So this, the matching of the students to universities, hospitals, to doctors. All these things are situations where every individual has some self-interest, right? So the hospital wants to get the best doctors, the university wants to get the best students, and the students also want to get into the best university. So you need to have some sort of a stability in the matching that you are doing. It should not happen that the university and the student would like to break away. So after this, the declaration of the results are made, the assignments are made, they will break away and go to a new assignment. That should not happen. That is the idea of stable matching. The idea of stable matching is also used in human organ exchanges, and this is a very exciting area. So kidney exchanges, so you know that kidney, the human, a typical human being can survive with only one of the kidneys, and depending on various things like maybe you want to donate one kidney to one of your relatives who have lost both the kidneys, but you do not match medically. So there are lots of things that blood group and tissue type and so on that you do not match, but you are a willing donor. There might be somebody else who is also looking for a kidney, and their relative also does not match. So this donor and the patient pair, you can consider as one individual who are actually looking for a donor. So if you have a situation where your relative can actually donate to that patient, and that patient's donor is also medically able to donate you, then you are actually saved. Both these lives will be saved, and that is exactly what this kidney exchange algorithms do. Maybe you have a cycle where you can donate all these things, and then finally you have all this person's lives saved. So how do you do this? There is a huge amount of literature, and there are, in certain countries, there are algorithms run by the nation which actually runs this kidney exchanges or organ exchanges things. Federated learning, so this is a new paradigm. So in federated learning, so the Google keyboard that you use, you can see that the moment you start with your Google keyboard, it's actually not giving you suggestions or autocorrections that well, particularly if you're using some Indian languages. But over time, it is learning, getting smarter and smarter, right? So how does it do? Maybe there are different other users who are also using the same language, and in a certain way, they are collecting all this information, the learning at a central place, and that language model is then pushed into each of these devices, right? So this is the whole idea of federated learning. Now, the question is, again, why should people contribute? So maybe this is a very simple example, but think of a medical situation where everybody has some medical data and you want to learn the right model for disease prediction or disease recovery, but that might require a lot of data. So some hospitals which has a lot of medical data will only contribute to that federated learning process if they get some payoff out of it. And if you just use the federated learning as it is, there might be a possibility small hospitals which do not have sufficient data, they might just free ride on the data of the others. So this is also an exciting area of incentivizing federated learning that's happening for the past few years. Peer grading, let me talk about that offline if you are interested. Airline scheduling, so many examples where you can actually have this kind of a strategic behavior. At the same time, you have certain components of learning or artificial intelligence, but you also need to take care of this fact that people are self-interested, and all that you can get is an equilibrium outcome and not a optimal outcome. Yeah, go ahead. So game theory is about multiple players. So yeah, so we are trying to give an equilibrium.
It is only for 2 participants. That's why it is
Oh, no. So the examples that we have just given is only to illustrate, because I can only show 2 players here, otherwise it will get confusing. So yeah, so any number of players you can include. Any other questions? Okay, so yeah, I'll not get into any further details. Just want to show that there are certain, so in our group, there are certain interesting areas of research in all of these areas, but in particular, this auctions, which we have recently worked with 2 of our students. So if you are a student who are interested, I urge you to take a look at our group's website, talk to some of the students. I can see Drashti there. Can you just, yeah, so you can feel free to talk to them during the, I'll definitely be around, but also talk to them. Vidit is also there. Can't see anybody else. Ram, no. Okay, so yeah, so please feel free, and also attend all the student poster sessions, student talks. So there will be much more interesting things, and I welcome you all to take a look at those group websites and talk to all of us. Thanks very much for your attention.
Thank you, Professor Soprava, for such an insightful talk, very interesting examples. We would like to express our gratitude to Professor Soprava with a token of appreciation. I'd like to request Professor Bhaskaran to do the honors. Can we have a round of applause? Thank you, sir. I hope you all have been enjoying the event so far. It's time to break for tea. I have a few announcements here. So the first announcement is for the participants, those who have not registered yet. They can register in the break. Important announcement for outstation participants. Outstation participants need to collect the travel allowance form and submit it with all the signed bills tomorrow. There is one more announcement. Those who are interested in knowing about the admission procedures of MTech, MS, and PhD, Professor Ajit will be there at the admissions desk. You can contact right outside. Okay, so grab a cup of tea, stretch your legs. I encourage you to engage in some conversations. The speakers will be around. Take advantage of that fact. I'll see you after 20 minutes at 11 o'clock. Thank you.